Hello everyone. In this video we're going to solve exercise 29 of chapter 4 of the lecture notes. The goal of this exercise is to check whether you've understood the notion of a group, and here we use an example of a certain set, the rationals equipped with a certain operation. We just need to check whether it satisfies the different axioms of a group. So please stop the video here, try to do the exercise on your own, check at the definitions again, check the examples we've done together, and only once you've exercise or you're really stuck, come back to the exercise and see with me what the solution is. Okay, here. So in this exercise, we have the set Q of rationals, and we have equipped it with a certain operation that we are denoting by this strange symbol. And the operation is such that if you put A and B as inputs, the output is A plus B plus 2AB. And the question is whether Q equipped with this strange operation is a group. So the only thing that you need to do this exercise is to know whether this forms a group. So you need the definition of a group, which is the following list of 4 axioms, right? The first axiom is that Q should be stable, is stable under the operation that we have just defined. So that's the first property. Second property is that the operation is associative. Third property is that the operation admits an identity element. And the fourth one is whether or not all elements are invertible. All elements are invertible. So these are the 4 properties that we need to check, and it's suffices to show that one of them is not satisfied to show that Q equipped with this operation is not a group. So the first thing you need to do before starting any computation is try to assess out of the 4 properties which ones are the easiest to check and which ones are the most complicated one. So you end up with the most complicated one, okay? In case one of them is not satisfied, you finish the exercise. So here, and it's generally the case, associativity is the most tedious one to do. So you want to leave that as the last thing to do, right? This is tedious, might not be hard to do, but it's just a long computation. And in this case, the other 3 are easy or easy. Let's put this straightforward, okay? Easy to do, this takes a bit longer. Okay, so we should start with checking property number 1, then 3 and 4, and last associativity in case all of the properties before are satisfied, okay? Okay, so let's start with stability. Well, the only thing that we are asking here is whether if A and B are both rational numbers, then A plus B is a rational number, right? The sum of 2 rationals is a number. 2AB is also a rational number. So if we do the sum, the operation, the whole thing together, it's also a rational number, okay? Here you could go faster than this and say the stability follows from the fact that the rational numbers are a field. Stability follows from Q being a field, if you know what a field is, being a field, okay? So it means that it's stable under sums of rationals, multiplications of rationals, and all the other properties that a field should have, okay? But that's the only thing we need here. So we have stability, okay? So Q is stable under alpha. That's the first thing to check. Second one is now we want to check whether or not alpha admits an identity element, okay? Because we want to leave associativity since it's the most tedious one for the end. Okay, so what's the definition? Let's come back to the definition of an identity element. We want to find E, belonging to the rational number such that for any A that you take, any other rational, if you do the composition, then this is equal to A again, right? And this should be true in both directions, A, E. Okay? Good. So just one remark that we can do here is that remark, let us put this here as a remark. Our definition of the operation that we have here is commutative. You see that if I exchange the order of A and B, this is the same as B, A. Okay? So the operation is commutative. This simplifies just a little bit what we have to do, because then it means since it's commutative, we only need to find an E that satisfies the first part here, and will automatically satisfy the right-hand side as well. Okay? Remark, alpha is commutative. Okay, so now we just need to solve the equation. Now we just plug what the operation means. So we want E plus A plus 2EA, that should be equal to A, right? Can just solve for E in this equation. So we simplify the two A's, and we get E factor of 1 plus 2A is equal to 0. And this should be true for all A. So the only solution is E equals 0. Okay, that's the only way in which this can vanish if we're doing this for all A. For all A belonging to Q. Okay, so therefore the identity element is 0. So alpha admits 0 as identity element. Okay, so that's the second thing that is satisfied. Now we turn to the fourth property. Now we want to check whether all elements are invertible. So fix some element, fix A belonging to Q, and we want to find some other number. We want to that we can call A minus 1, also rational, such that if you use A and you compose by A minus 1, or if you do it in the opposite direction, it should be equal to the identity element, which is 0, right? Okay, and again, since it's commutative, it's only enough to show this, right? It suffices to show this part, and automatically you will have the right-hand side here, because the law is associative. Okay, so now we just need to solve for this again. Let's write it down. We have A plus A minus 1 plus 2A A minus 1 equal to 0, and our unknown that we want to solve is A minus 1, so I just will write it down by passing A to the other side. So we have A minus 1 factor of 1 plus 2A. This is equal to minus A, and therefore A minus 1 is equal to minus A divided by 1 plus 2A. Okay? So this shows that if you choose A, you can find an inverse such that if you do A operation A minus 1, you find 0. However, you need to be careful here, because you are dividing by 1 plus 2A. So in fact, you cannot do this division for any A belonging to the rationals, right? This is not possible except if A is equal to minus 1/2. For A equals minus 1/2, the division here is impossible. So in fact, what we see here is that all numbers are invertible except minus 1/2. So minus 1/2 is not invertible. And therefore, this ends the exercise here. It's not invertible. Therefore, Q equipped with this operation alpha is not a group. Okay? And that's the conclusion. Now, since this is just for the sake of it, we can check as well the associativity. Is just a small exercise. It's completely useless in this case because we already know that it's not a group, but just for the sake of it, we can also check what the associativity is, okay? So associativity, we should check what happens if we're doing A composed with B composed with C, and we should try to compare this with what happens if we're doing the opposite, right? A composed with B, and this whole thing composed with C, okay? So we can just apply the formula, and for example, this, by definition, is equal to A plus B composed with C plus 2A B composed with C, right? And now I plug the expression of B composed with C, so that's A plus B plus C plus 2AB, right? That's this part here corresponds to this, okay? And plus 2A, and now I just develop this 2AB plus 2AC plus 4ABC, okay? Now just look at this expression. So now we want to wonder whether this expression is going to be the same as the expression with putting the parentheses on the left. There is one thing that you can, as a remark here, that you can notice is that in fact this expression, the rows of A, B, and C are exactly the same. First you have A plus B plus C, right? This part here. If you exchange a B and an A of order, that doesn't change anything to the expression. Here, it's also true. They all play the same role. You have all couples AB, AC, and BC. So actually I did a mistake somewhere. Sorry, here it's not AB, it's BC, right? That's a small mistake that I did. BC here. And in the last expression here, also ABC play the same role, okay? So the expression does not distinguish between A, B, and C. So therefore, only with this remark, you can notice that this expression has to be the same as, therefore, any way of writing these three symbols, of combining them, A, B, C, with the parentheses here, or A, C, B, or B, whatever you want to do, A, and so on, all of them are going to be equal because the final expression that we found here does not distinguish between A, B, and C. So that's a nice structural way of trying to avoid some computation sometimes, okay? But in any case, I insist here, associativity was not something that you had to solve because you had already realized here that not all elements are invertible, and therefore our initial question, whether it was a group, the answer was no, okay?